last time, so we were discussing microcanonical ensemble. And the physical situation that we were considering was that of a system. By the way, it doesn't have to be rectangular. I keep drawing, and in books also you see this shape, but it could be like anything. It doesn't. So it's a system that is, well, there are two systems A and B which are in thermal contact with each other, and the composite system is thermally isolated. And we have taken both these systems to be short range interacting. So there is no, I mean, the particles interact with one another with a force that has got a finite range. And then what we were after was the following. So we considered the situation in which the composite system had n particles and volume V and some energy EC lying in the range E and E plus delta. Let me just see my notation, I think. Okay, so that's the energy of the composite system, and under the assumption that these two systems are short range interacting, we can say that in the thermodynamic limit, when we consider the number of particles here and there to be very large, we can neglect the surface contribution relative to the volume contribution, and therefore we have the total energy given by the sum of energies of the two systems. And since somebody was, at least there was one person who asked me about the number of particles of each of these. So they are N1, V1, E1, that's the energy of the first system, and N2, V2 and E2. Number of particles, volume and energy, they of course satisfy the constraint N1 plus N2 is equal to N. V1 plus V2 is equal to V, and E1 plus E2 is equal to EC. Okay. And these two systems are in thermal contact with each other. This means that they are not allowed to exchange particles, or I don't allow this partition to move back and forth. I just allow the energy to fluctuate, to be shared between the two systems following this constraint E1 plus E2 is equal to E. And as, sorry. That's how I construct, How do I know, sorry?
The systems are in thermal equilibrium with each other. From the set of equations.
No, I do not know whether they are in thermal equilibrium. I am asking the question, if they are in thermal equilibrium with each other, what is the condition that ensures that the system, or the underlying condition that says that the system is indeed in thermal equilibrium? I do not know whether they will ever come to equilibrium. If I take some two like arbitrary systems and bring them in contact with each other, I may ask, is the system in thermal equilibrium? Or how long does it take for the two systems to come to thermal equilibrium? Do they ever come to thermal equilibrium? These are very pertinent questions, but within this framework of equilibrium statistical mechanics, we are not addressing those questions of relaxation, how do they come to equilibrium and so on. We are asking, if they are in thermal equilibrium, what is the condition that I should check to find out that they are indeed in thermal equilibrium? And we will see, we know from thermodynamics that if they are in thermal equilibrium, the two systems have to have the same temperature. So we want to derive that, and this will that condition, and this will also allow me to define temperature in terms of the microscopic variable, microstates, measure and so on. Okay. No, now they are interacting. They are interacting in the sense that, see, they are interacting, that is why there is some exchange of energy between the two. They are interacting in that sense.
See, operationally N1 and V1 are fixed, but E1 can change because some of the energy can go to the other side, but E1 plus E2 is fixed.
Okay. So maybe this is, don't know how to say it. So you see this, like I kept on saying that, you know, this partition is not allowed to move back and forth, and therefore V1 and V2, they are individually constant. So this is a constant, that is a constant. This is a constant, that is a constant. On the other hand, E1 and E2, these two quantities are not constants. They are allowed to fluctuate subject to the condition that E1 plus E2 is equal to EC. And we are trying to find out how many microstates are possible for the composite system under these constraints, that there are two systems in contact and the energy is allowed to fluctuate, how many microstates are possible. And as you will see that, you know, this treatment, like the way we are going to do it, or, you know, some, we did do some part of it yesterday, it can be generalized to other situations. For example, you may say, oh, I don't allow the energy to fluctuate, but maybe the number of particles is not constant, it is allowed to change, or this partition is allowed to move back and forth, so that there is some volume exchange, so to say. You can do the same treatment, but like traditionally, like energy, because we want to, why we do this example, because we want to first of all check this condition that if the two systems are in thermal equilibrium, the temperature of each of the two subsystems is equal to one another. Okay, that's one, and this would allow me to give, I would not not a model, I would say a framework. It allows you to define temperature. Like as I said, you can think of it this way, that there are two systems that are in contact with each other, or what you can do is that you can think of just one system and there are two, you know, different parts. They are, of course, they are part of the, say, I can also do like this. There is one single system. And what I want to do is that I know somehow that the system has come to thermal equilibrium. I want to find out the condition, and so thermal equilibrium means that, you know, the different parts of the system have the same temperature. I want to get that out of the, you know, the formulation of the problem in terms of phase space, microstates and so on. I want to establish the condition that suppose I break it up, not just 2, you can do it 3, 5, 7, etc. Whatever you do, I want to see that the temperature of each and every subpart is the same.
Yeah, actually I have one major problem with statistical mechanics. Generally in quantum mechanics or in Newtonian mechanics, the target is first we develop the construct equation operation, and then we evaluate the displacement. The knowledge of displacement will help you to find out all the physical quantities associated. Similarly, in quantum mechanics, the wave function is associated. But here, what is the objective of?
Here also I am trying to do the same thing, that I know the equations of motion. So that your question gets recorded.
Okay.
I know the equations of motion of the particles constituting this system. I know the equations of motion of the particles constituting this system. I know how to describe them in terms of motion in phase space. I know how does the phase space density evolve as a function of time, because the individual particles are moving around according to Hamilton equations of motion. I know that this phase space density may evolve to a state in which it no longer changes as a function of time, and therefore, according to the definition that I had written down the other day, the system has come to thermal equilibrium. I am taking exactly the same point of view, that I am starting with equations of motion, but
what I'm expecting at the end.
I am expecting to prove that at the end, the temperature TA will be equal to temperature TB. That's one. Secondly, what is this temperature? I don't even know how, I know how to measure it. I can stick in a thermometer and I know that TA is going to be equal to TB, because the system is in equilibrium. Okay. So my first aim is to establish this condition. Secondly, I want to interpret this temperature in terms of the phase space density.
You are defining, you want to understand the temperature in terms of phase space.
You know, the picture that I had set up, within the framework of, see the temperature.
The displacement or what is the wave function equivalent here in statistical mechanics?
So wave function equivalency, this is a classical system. I am describing individual particles in terms of Q and P. Okay, so this is the classical setting. In the quantum setting, I will not be able to discuss the motion of individual particles in terms of q and p, because if I am able to tell you q with infinite precision because of the uncertainty principle, I won't be able to tell you. With
Sorry, I did not frame my question properly. What I am expecting is, once the equation of motion is set, is it the temperature you are expecting as the solution of your equation of motion?
The temperature not as a solution, but it should come out as a quantity that may be interpreted in terms of some attributes of the motion. It will not come out in the sense that I am unable to write down at the moment. I am unable to write down how the temperature, some equation of motion for the temperature, but it should come out in terms of the microscopic quantities like q and p. No, partition, see, no, I would say that at the individual level, you have to first define how are the particles going to move around in time at the individual level of particles. So, it could be that the particles are classical, it could be that the particles are quantum mechanical. At the moment, I am treating the case where individual particles have classical equations of motion dictated by an underlying Hamiltonian. It may so happen that in some situations at the individual particle level, you do not have classical mechanical laws of motion, but quantum mechanical laws of motion, and that would go into defining the phase space. But now I have taken the first step. So, the first step is to identify whether the system is classical or quantum mechanical. This is before I do statistical mechanics. Okay, statistical mechanics has nothing to do with whether it would not be able to tell me whether the system is classical or quantum mechanical. So, that I have to decide what kind of system I am dealing with. Like, is it a system of bosons or fermions, electrons or galaxies or a glass of water or my mobile phone? What is the system? That depends on. So, I think I had mentioned this while during my lectures on dynamical system, that there are several levels of description. That so first you have to define the system. That statistical mechanics is not going to do. First you have to define the system. Which system are you interested in? What are the underlying equations of motion? That you have to identify. No, actually I should say the first step or the 0th step, the 0th law is, first you have to identify, first you have to get interested in a phenomenon. What is it that I want to do? Okay, first, that's the first thing. Before, even if you come, before you come to equations of motion, first you have to, there are so many things going around in this world. I have to single out one phenomenon that is that I am interested in. That's one. Secondly, I have to decide whether the system is classical and quantum mechanical. How do I make this decision? On the basis of some physical equation, or like another possibility is that I say that the system is classical, I do some calculation, I get an answer out of it, answer for a measurable quantity, and I go and do my experiments, and if I see that they match, I would say, I won't be able to say for sure that the system is classical mechanical. I will say that my assumption it's consistent, like okay, okay. So, this statistical mechanics cannot tell me whether the system is classical or quantum mechanical. That's for what are the equations of motion. Suppose I tell you the phase space density, I just look at it and say, oh, this is it must be Schrodinger equation. That I won't be able to do, because these are different levels of description. Sure.
Since she was asking, is this a model? No, it is not a model. Model, let's say, would be operationally defined in terms of the Hamiltonian. Different models will correspond to you have neon atoms interacting with each other. There's a particular type of interaction that goes into the Hamiltonian. If you have carbon dioxide molecules, it's a different. So these are different models. What Shamik is developing is a framework which will apply to all models.
Yes, exactly. So H is given to me, like as I said, H equations of motion. If it's a quantum mechanical, it won't be the Hamilton equations of motion, but those things are given to me because those things have gone into defining my phase space, motion in phase space and so on. Okay, and I had a Poisson bracket. If it were a quantum mechanical system, I would have had a commutator. Okay, so the definition of rho would have been completely different. I don't know what Q's and P's are. It's not possible to do it. So I want to first show, as Constancy said, that when I know that from experience and also thermodynamics tells me that if the two systems are in thermal equilibrium, TA has to be equal to TB. How do I get that result out of it? That's one. And secondly, how do I interpret this temperature in terms of, so what I am given is Q's and what I am given are Q's and P's, and I have built this phase space, this picture of phase space, points are moving around. I want to interpret those things in terms of those quantities, rho, Q and P. Okay. Okay, so now what we are interested in is, okay, so NV, so this is the macrostate of the composite system. So for the composite system, I have told you that it contains so many particles and the particles occupy a total volume V, and this is the energy of the composite system. Sorry. So now what I want to do is I want to write down all microstates which are possible for this composite system, which are all consistent with this given macrostate. And I know that the system is in thermodynamic equilibrium, microcanonical equilibrium, because that's a setting that we are after. Okay, and I had written down this expression for the number of microstates. I keep saying number, but it's actually the volume of phase space occupied by accessible or consistent microstates. I do not personally think that it would be so much of I don't know, sin or something if you say number of microstates, provided you know what they are. If the number is less than 10 raised to number of, what is the 10 raised to 9? This I don't. What is it? Yeah, I don't know this. So provided you know what, so maybe for a specific example there, I don't know exactly what is 10 to the 9, but you understand the thing that Q's and P's are continuous variables. So in that sense, it's I mean technically, I mean one should not be talking about number of microstates, but so long as you know what you are talking about, I mean you should continue. Q and P treated as a function. These are, sorry?
That is number of particles in the physical system, what you are telling that power by
Yes.
So that is different here. Here it is phase space particles.
No, but when the particle is large, naturally number of Q's and P's will be large.
Yeah.
So they are related somewhere. But once we go to the concept of these Q's and P's, then the concept of particle actually goes away. Then we cannot think in terms of number of particles.
I mean, okay, number of degrees of freedom. The right way to think about them is number of degrees of freedom. How many generalized coordinates there? Because it could be that the system is subject to some constraints, and therefore the number of degrees of freedom could be smaller than the number of particles. But I don't know this 10 to the 9, so that I'll have to check. So maybe, I mean, it's not that everything that's written there has to be taken. So one has to look at it carefully, but maybe it's okay. So what's the volume of the accessible phase space for the composite system? So that we had written down an expression for. So that's given by, I think it should be EC. So let me write this instead of writing EC like over and over again. Let me just call it E. Or let me write it this way. So this I have already written. So for the composite system, the energy lies in a small range, E and E plus delta. The delta, if you can find E with infinite precision, you just put delta equal to 0 and that's it. So So this will be equal to, so what will be the total number of microstates? That's the product of the number of microstates for system A and system B, and system A can have many different energy values, and correspondingly system B will have energy values satisfying this constraint, and then I have to sum over all possible values of the energies of system A. So that's just gamma 1. So this is the number of accessible phase space volume for system 1, and this is for system 2. So of course as soon as I tell you the energy of system 1, the energy of system 2 is fixed because there is a constraint, and I have to sum over all possible values of the energy EI. That's for system 1. Somebody was asking me how, who was that, somebody was, so could you figure out how does one do it? It's just, you know, what you do is that you just break it up into levels of separation delta. Yes, exactly, 0 to E. It's just some careful bookkeeping, I mean, and that this can be done in more than one ways. See, when or you can write it also as an integral. I have written it as a sum, but I have to really the energy of this system is a continuous variable, so I should be really integrating over all possible values of this one and correspondingly that one. I can also do it as a sum because I have this luxury of using the imprecision delta in discretizing my energy level. But the system is still classical, there is no quantum mechanical, so don't think of the energy levels as really the solutions of some Schrodinger equation. Nothing like that. And then we had said that, well, this is a positive quantity and so is this one. So this is a sum of many like positive quantities, and then finally we had come to this. So I had made a statement about the entropy being proportional to n, so that I may need to make some correction for. But let me just get to the final result. I'll come to that in a few minutes. But let's first finish this part. I mean, what we had written down. You can write down n here or n1, n2 here. I'm just E2 bar V2, where of course I should not write like this. Well, E1 bar and E2 bar, they are not independent of one another. E1 bar and E2 bar, they satisfy that constraint, that's equal to E, the total energy.
V1 all are constants.
Yeah, yeah.
Is the parameter only, no?
Yeah, V1, V2, N1, N2, these are constants. You don't have to.
V will be the parameter.
V is equal to V1 plus V2.
Is entropy function of V because V is not changing?
You don't have to write. If you don't, it is a function of V for a given system. It is a, but in this particular
We fix the V.
so you can forget about V. I don't need it actually. Similarly, N, entropy is really a function of NVE because
Another V will be.
yeah. So you can forget about it. If this is confusing, forget about it. The only variables that we are considering in this setting is the energy. Okay.
What's the EI corresponds to?
So this I haven't told you. I've just EI corresponds to.
Suppose I is equal to 1, I is equal to
Okay, so what I've done is the following. See, this is the phase space of system A, and this is the phase space of system B. Okay. Now, system A can have many different energy values. Okay, so let's say here there are some energy surfaces. So like many different energy values are possible, and here also many different energy values are possible. Okay. So they form a continuum. It's not that they're some discrete like energy level. So what I am doing is that in order to construct the microstate for the entire system, I have to choose a microstate from here with some energy EI, and I have to choose a microstate from there with some energy which is E minus EI, because the total energy has to be. So I choose here, and these two I have to just multiply. How many microstates are possible? Let's say you have two coins, so you are tossing both of them together. How many heads are possible for the? How many heads are possible for this? How many heads are possible for that? I am just doing this. So that's why there is a product, and now I have to sum over all possible energy values here. So that's what I am doing. So I think somebody asked me, what happens if you have a long range interacting system? The problem with a long range interacting system is the following, that you cannot write down the energy of the composite system. So in case some of you don't understand this, you don't have to worry about it. This is a specific question that somebody had asked me. So let me just clarify clarify this point for him and also those who are in. See, for a long range interacting system, I cannot write down the energy of the composite system as the energy of system A plus the energy of system B, because there is going to be a significant contribution coming from the interaction between particles, one of which is located in A and one of which is a pair of particles, one here and one there. And because it is a long range interacting system, that some particle which is here in the bulk is going to interact with another particle which is there in the bulk, and it is not that there are only particles across the interface that I have to take care of, because this is a long range system. It could be that the interaction gets weaker if the when the particles get very far apart, but it is not 0. So then there is one E12, let us call it like this, E12, and then you see that if I tell you E1, E2 cannot be expressed in terms of just E1, because there is this K. So I cannot write down like this gamma 1 of EI, E minus EI. So does that mean that the whole thermodynamics breaks down for long run? It's not like that. You can do, but you have to do a different treatment. The treatment is it has to be different from the. I cannot see this. But the fact that the total energy is constant and this is a these things will go through, but when I write down the number of microstates, I have to be more careful in doing so. Okay, so let me just get this. And I have not told you how to determine E1 bar and E2 bar, but I have told you what they are. They are the values of. So what are E1 bar, and well, if you know E1 bar, you know E2 bar from that expression. So what is E1 bar? It is the value of E1 for which this quantity is maximized. That's how I defined it. That it's a sum of positive terms, and it could be that there is a particular value of EI for which this product has got is maximized. So we will show that it's just given by del of it's again I can write it down right away. So how is EI bar defined? So you can, I want to use the same notation. So can I turn on the AC? Okay, thanks. See, this is just gamma 1 of, oh, 27, no problem, make it 23 or something. Thank you. Gamma 1 of E1, gamma 2 of E2 equal to 0. So I have to maximize this term subject to the constraint that E1 plus E2 is equal to E, which implies that E is a constant, the delta E1 is equal to minus delta E2. So these two quantities cannot be, when I am doing the variation, they cannot be varied independently of one another, because it has to, if I increase E1, I have to decrease E2 proportionately such that the sum it doesn't, and a solution of this equation subject to this constraint is E1 bar. I will come to that in a minute, but let us first look at, in fact let me just write it right away. So until now it is clear, right, how do I get this one. Now let us come to the definition of E1 bar the way I have written there, and let us just do that small little algebra which is there. We don't need this one. So if you do this algebra, you know, instead of maximizing gamma 1, so gamma 2, what you can do is that you can take the log and take the maximum of that also, like, you know, or you can just do it this way. It will give you gamma 1 delta gamma 2 plus gamma 2 delta gamma 1 with corresponding factors of E1 and E2, and finally what you get is this one, del del E1 of log of, you get the log because what you would get is gamma 1 delta gamma 2 plus gamma 2 delta gamma 1 equal to 0. You divide throughout by gamma 1 gamma 2, and therefore you would get delta gamma 1 by gamma 1 plus delta gamma 2 by gamma 2 equal to 0. I think you must have seen it in like error calculation in lab. I mean, how many, this is just for curiosity, how many of you are taught how to do error calculation in the experiments, in the BSc experiments? No, the older ones are saying yes, but how about the, because somehow I gathered that it is no longer taught, somehow it is considered, huh? They don't make errors. Huh? Also the instruments have become very smart, I mean they also don't make errors. Oops, sorry. And of course, E1 bar and E2 bar, they satisfy this constraint that E1 bar plus E2 bar is equal to E. If you do that calculation, you straightforwardly get this one. Okay? And let's look at this equation and try to interpret it. So you recognize what this log gamma 1 of E1 is. If I multiply by K, that's going to give me the entropy of the first system at energy E1. Okay. So if I do that, or so this is just del of S1 of E1 del E1 bar is equal to del of E2, del E2 of S2 of E2, there is no bar here, to be evaluated at E2 bar. Okay. And E1 bar and E2 bar are values such that the entropy of the entire system is given by the sum of entropies of the two subsystems evaluated at E1 bar and E2 bar respectively. We have got an equality, right? Equality of a quantity that refers to the system on the left and a quantity that refers to the system on the right. Right? Because this quantity depends only on the properties of the phase space properties of the system A, and this quantity depends only on the properties of the system B. Right? And they happen to like obey a constant, that's because of the conservation of energy. But that's it. So now we know that what we are after. We wanted to show that there is some quantity that depends entirely on the properties of system A and some quantity that depends entirely on the properties of system B. If the two systems are brought in contact with each other, this quantity becomes the same for both the, they becomes equal, not same, like this quantity takes up the same value for both the systems. And here I seem to have a quantity that depends only on one on A and one on B, and I know that the system is in equilibrium. So you would say that, well, this must be the temperature, must be related to the temperature. It doesn't have to be exactly the temperature. You would say this must be related to the temperature of system A, and this must be the this must be related to the temperature of system B. This is how I should define my temperature in up to some constant factors, and in fact this is the temperature of the two systems. So if I define if I define my temperature as 1 by T, that is, why it is 1 by T? For dimensional reason, okay, that it has to be of that form. So if I define my temperature in the following way, so this is my definition. If I define my temperature this way, then I see that what this is telling me, that E1 bar and E2 bar are those special values for which the two sides have the same temperature. T1 is equal to T2. Okay, and this is, and let's look at this equation. So what it is saying me is, what it is telling me is that for a given system, what I do is that there are these points moving around. I draw the phase space equilibrium. So rho is constant. I know how to define S, that's log K log E. I just take the derivative with respect to, and that gives me a quantity. It's important to note that this quantity or this quantity here, it depends entirely on the properties of system A. It makes no reference to system B, because it is a property of the phase space coordinates and the density of system A alone. Okay. So this allows me to define the temperature and also to show that Ta is equal to Tb when the system is in equilibrium. Now I could have defined it as 1 by T square or e to the power T to be like that, and then also I would have gotten e to the power Ta is equal to the power Tb, and therefore Ta is equal to Tb. But it turns out that if you take other definitions of temperature, first of all there is this dimensional problem, and secondly here it's not that we will be content once we have derived this result and we go back. We have to recover the whole of thermodynamics, all the laws and so on, and this is the definition that one has to follow. I mean one has to choose, and like everything falls in place if we choose this definition. There was something that I was planning to say, but now I forgot what was it. Okay, and what is this? And now let's look at this equation, or interpretation, physical interpretation of E1 bar and E2 bar. What does it mean in terms of microstates? So what it means is the following, that given that the total energy is constant, this may exist in many different microstates, this may exist in many different microstates, but bulk of the microstates here are going, see, each microstate has got a given value of energy. It should be clear, right? That's fine, right? Because a microstate means I tell you the values of Q and P, and as soon as I tell you the values of Q and P, you can insert those values into the expression for the energy, the Hamiltonian, and I know the energy of that microstate. What this is telling me is that there are many different microstates possible here with different energies, here also too different energies, such that the sum is constant. But it turns out that bulk of the microstates, most of the microstates here have got the energy equal to E1 bar, most of the microstates here have got the energy equal to E2 bar, such that the entropy of the total system is like that. And how do I define like E1 bar and E2 bar? They are those special values for which the derivative of the entropy with respect to energy for the two systems becomes the same. Is this clear? I mean, this is no way telling me that you cannot have a microstate for system A for which energy is not equal to E1 bar. It is not telling me. It is telling me that as the system size becomes larger and larger, most of the microstates will have this energy E1 bar, most of them will have microstates E2 bar. There will be some fraction of microstates, some small number of microstates with energy not equal to E1 bar, not equal to E2 bar, yet satisfying that constraint, and that the relative fraction will keep on decreasing as you make the system larger and larger. It's okay, because you remember how did I derive this expression? I said that AC is a sum of many terms, and I picked up only the largest term. So that means the other terms they cannot just vanish. So it's just saying that the most probable, not most probable, like bulk, most of the microstates are in the. If you repeat this, this experiment of choosing a microstate here and a microstate there for thermodynamic systems, such that the energy is some value here and this has the complementary value, you will find that if you repeat it 15,000 times, most of the time those have energy E1 bar and these have energy E2 bar. You want to make a comment? No.
Well, in terms of numbers of microstates,
Not
you, what you said correctly is that the bar criterion identifies the ones that you will access in a
Thermodynamic system.
But the other microstates, I mean, so is that true at the level of logs?
Yeah, true at the level of logs. I mean, it's just
taken a log,
exactly.
say precisely number of
It's
microstates, that may not not have value, but once you take the log, it's
because the log is, you see, it is
true at the level of log divided by the volume. Then it's going to.
but at the, I mean,
But effectively what you're saying is correct.
that there, okay, let's look at it this way. There will be some microstates with different energies for both the systems. Because S of E was log of gamma, that's what I do, log of gamma E, and that was log of sum of many terms, and I picked up the largest one. That doesn't mean that the other terms are vanishing. They are there. They will add some correction. That correction becomes, let me put it this way, that correction becomes smaller and smaller as you go to the thermodynamic limit. That
Because of this constraint, that total energy should be some. We have so many choices about E1 and E2. If we opt the choice E1 bar and E2 bar, the corresponding number of microstates is the highest.
Yeah, okay, you can put it also, yeah, that's also the, you have, so that's why I kept on saying bulk, that's why, that the system is, if I do this, if I somehow had a way to find out which microstate the system is in, more often than not it is in a microstate for which the energy is E1 bar, more often than not it is E2 bar. So I think it is somehow in some textbooks, not in Carson one, in some textbooks they somehow give the feeling that when the two systems equilibrate, you have just microstates with energy E1 bar, you have just microstates with energy E2 bar. It's not like that. There are, I mean, because they don't violate any of the concepts. There are other microstates, but that's the correction that you get because of that is subleading, or the way.
By reading that, we sometimes have a feeling like that. It is not written like that, but we have a feeling like that.
So that's why I wanted to clarify that I don't know why they write like that, but it is somehow I have a feeling that in Pathria it's stated in that manner, not in Carson Wang as far as I could tell. But it's important that and I think this is especially for teachers, I think this is something that I would like to emphasize, that this algebra etc., these are trivial. I mean, you don't need even calculus of variation or very ddx of tan hyperbolic x. I don't even know what it is. I have to really work it out. You don't need any such thing, but it's important to highlight or emphasize the physical situation. That if you think about it, I mean, you bring two systems, only some microstates are there, and somehow gives the feeling that the other microstates disappear. I mean, they cannot disappear. I mean, they are there, but they're okay. So what is the next thing that I should? Acha, let me talk a little bit about this postulate of equal a priori probability, and relate to this. Is it mixing and ergodicity? So the way we defined a microcanonical equilibrium, if you recall, what we did was we said that there is this. Is this clear, or you seem to have some questions? So please let's clarify them. I don't have.
No, actually, what it was about the temperature of the system. But it's not to be seen. That's what I was thinking.
Acha. So let's see how much did you, for example, this part is okay, right? This part is okay. And the variational thing that I had written down, that is okay, right? That's how I define E1 bar. Okay, that doesn't come out of it, but it's my definition. I am defining E1 bar to be the value of E1 at which the product gamma 1 gamma 2 is maximized. That's my definition. Okay, if I work that out, I see that I have a quantity quantity, I have this equation, like until now it is fine. Huh? This?
Yeah, actually I wanted to express temperature in terms of gamma.
Yes, that's what I have done. S contains gamma.
Then it's done.
Huh? That's what I was after. I wanted to identify a property of system A and a property of system B such that when the two come to thermal equilibrium, they have the same value. I have been able to define such a quantity T, and indeed T, temperature for a given system, depends only on the phase space properties of that system alone. Huh? That's how and you see here, as I mentioned when I talked about Boltzmann's definition of entropy. See here, all the information about how the particles are distributed in the phase space are contained, all this information is there, it's contained in gamma E. Gamma E contains the fact that the energy hypersurface is uniformly filled up with phase space points. Huh? That's how I define my microcanonical ensemble. Okay, so let me come to now. So this part is fine, right? And once you understand this thing, then canonical and grand canonical, they become somehow kind of trivial. I mean, you can do it. I mean, there's not much. You have to just take care of the fact that you have large system and do some Taylor expansion, and that's it. I'll indicate how does one go from canonical to microcanonical. So remember that we will also discuss this fact that you can go from one ensemble to like another by choosing a different set of independent variables. So remember in the microcanonical, for the moment just remember what are the natural variables, the independent variables in the microcanonical ensemble. It's the number of particles, the volume and the energy. Okay? And we will see that in canonical it's something different. By the way, before I go to postulate of equal a priori probability, you can see that suppose you have a situation where where you are interested in the following case, where the two systems are not allowed to exchange energy between the two. They can exchange particles among themselves, because you have three variables N, V, E. Either I let E to be exchanged or V to be exchanged or N to be exchanged. Can someone tell me that suppose I let N particles to fluctuate between the N1 will fluctuate, N2 will fluctuate, but N1 plus N2 is equal to a constant N. E1 is not allowed to fluctuate, E2 is not allowed to fluctuate, and therefore the sum will not fluctuate. And suppose I do this whole calculation, what will I get? I will get equality of some other quantity. No. So it must have some physical understanding. See, so this is something that I often. This is for students. What is temperature? Temperature. Del D. That is not the definition of temp. An equation cannot. It's. I remember because in my school I had a very good. We had a very good physics. History teacher. He used to tell me that, look, if somebody asks you, who are you, you should never say, I'm the son of my father. It's like that. You have to, it cannot be just del E of something. That doesn't tell you anything. And also dodo, etc. will not be understood by half of Indian population. Okay, so that's another problem. So then you say that, okay, I come from this place, and maybe you do some transformation. Okay. See, so what you would get is, you will get the derivative of S with respect to N, and you would find that this derivative is the same for the two systems. Or if you let V to fluctuate, you will get del S of del V, and that would be the same. So this would allow you to define what is called pressure. This is something we know, that suppose I let this guy fluctuate a little bit, what will be the equilibrium situation? When on unit area, I have the same force being exerted from this side as I have from that side. And by force on unit area, I know what is it. It's pressure. So it has to be that this formulation must give me the fact that when the pressures on both sides of this thing, they are equal, the system is in mechanical equilibrium. I would not call it thermal equilibrium, it's mechanical equilibrium, because force is, we have heard it many times during Professor Mukunda's lecture, mechanical system, force. Okay. So if the volume fluctuates, the pressure becomes the same. If the number fluctuates, then I will say, well, the situation will be, what will be the equilibrium situation? The chemical potential is the same. You say that the system is in chemical equilibrium. You see, the same formulation allows you to play around. You just, it's up to you. You choose this to fluctuate or that to, one at a time. Huh? If you make two at a time, I mean, you can do that, but it becomes more.
Not there in the literature, the volume fluctuation kind of.
Not there, but you can do it. I mean, I usually, actually, it is. I mean, in my lecture, in my class, I usually ask my students to do this because of the following reason, that in canonical, in microcanonical, there is no mention of chemical potential. In canonical, there is no mention, and suddenly in grand canonical, it pops up. But it's not like that. I mean, it is there. It's just the physical situation that you are considering. You are not allowing number to fluctuate. You may allow number to fluctuate. There is no problem. I think in Carson Wong there is an exercise.
The number fluctuation, the energy fluctuations will come automatically. So number and energy has to be fluctuate together only.
What?
If we exchange two particles which might be containing different energy.
If numbers fluctuate, energy will also have to fluctuate automatically.
I don't know whether they have to fluctuate. I mean, I can restrict myself to those microstates that doesn't tell that do not.
That is possible, but in practicality it is not possible. That's why the grand canonical principle might have.
Okay.
Numbers fluctuate, energy has to fluctuate.
Like is it one precludes the other?
Logically, Shamik is right. I think you can fluctuate numbers, yet keep the total energy of system 1 the same.
Yeah, you put the constant.
As that of
yes. I can, it becomes, like as I said, it becomes messy because now you have to restrict yourself to those microstates which allow numbers to fluctuate yet keep the energy constant. These constraints we will get rid of one by one. That is the utility in going for higher ensemble. Yeah, it would be difficult to do in practice, but in principle there is no problem. I somehow have a way to filter out those particles, I mean those microstates that have got the same energy, and then I can do it. Of course, I'll have to deal with delta functions, and as we have already seen one delta function. It becomes much like things become much more simple.
Casually, if you fluctuate the numbers, the energy will fluctuate.
Okay.
Casually, if you do that, energy will fluctuate.
If I do it without any constraint, of course you are right that it will fluctuate.
Sorry, I didn't understand what do you mean by fluctuating number of particles.
Fluctuating number of particles. So did you understand what does? So when I say fluctuations in the energy, okay, fluctuation. It's not one value. There are many possible values. This is okay. Suppose I say that n1 plus n2 is equal to n. I have to. I am telling you that you have to.
You have removed that barrier between A and B?
You make it. You make some holes. So then they can go back and forth. And one is the motion, that's the volume fluctuation. You make some holes, that's number fluctuation, or you make it what is it called? The one that conducting wall. So that energy can go back. Yeah, so gamma is a function of n, v and e, everything. So I mean when you write those equations, often it is good to write out in full, like you show all the dependence, but then depending on the physical situation you are considering, it should be like evident that look E is not fluctuating or V is fluctuating, and because these are the independent variables, N, V and E, these are the independent variables in the microcanonical setting. In the canonical setting, some other things will take the role of temperature, and then so we will see that for maybe I am jumping ahead of so N, V and E, this is for microcanonical, but then you get rid of E and then you have NVT, so that is canonical, you get rid of this, so you have VT mu. So the independent variables change as you make, and that makes the system lesser. I mean the constraint, the constraints on the system go on decreasing. But like let me not jump ahead of. Achha, let me come to this postulate of equal a priori probability. So I have it somewhere. Maybe this one. Achha, so you remember how did we define the microcanonical equilibrium? First of all, we said that an equilibrium state is one in which macroscopic observables or observables have mean values that do not change as a function of time. So if I do a measurement now, equilibrium very simply what it means is that if I do a measurement now, which is 12:30, and that halfway during the lunch time when so today we have a special lunch, and then also the value that it doesn't change. So this is just equilibrium. Okay. And the way we had derived it was that we had said that look, you have rho which is changing as a function of time, and if it so happens that the observable has a mean value that doesn't change as a function of time, that means rho itself, the distribution of the phase space points on the energy surface has got a time, the distribution is not changing. By the way, so like another misconception that many people have is, it's not that the points have become stationary. It's not like that. In the phase space, it's not that the points, the individual points have become stationary. The distribution is not changing. In every unit volume, there are two particles all the time. But that doesn't mean that those two particles are exactly the ones that were there at t equal to 0 and t equal to 10. So some come in, some go out, yet the distribution is not changing. That was the definition of equilibrium. And you remember how we had defined the microcanonical equilibrium? We said that okay, one solution of this equation, like anyways, I should be looking for solutions that don't depend on the temperature explicitly. Not temperature, time explicitly. So this is equal to 0 in equilibrium, and therefore this is in equilibrium. So one possible choice is rho is constant on the energy hypersurface. Of course, on the energy hypersurface, it has to be kept in mind that it is.
You mean to say that the time evolution is after equilibrium, it continues to be in equilibrium that way?
Yeah, equilibrium. No, it will continue. By equilibrium, it means that it has reached a state in which properties don't change. Particles have not stopped moving around. It will continue to be in equilibrium unless and until you do something. Just as every every particle continues to be in its state of rest, or if you unless here also every system continues to be in its state of equilibrium unless you do something on it to make it behave otherwise.
You said that NV and E are independent. So, but they're not in the same spirit as X and P is in classical mechanics, right? I mean, as he pointed out that there are cases that you could change N and E would change, like between the systems.
Of course, there are cases where, so here what you do is that, see, E, what he is saying is that E may, a posteriori it may change, but here I am saying while constructing my ensemble, these are the values, these are predefined values. I have told you that look, your energy is constant, your N is constant, your V is constant. Now you do whatever you want. It may so happen that okay, I don't give you this constraint that E is constant, so you choose some microstates with some N and some V, and you find out that E is not constant. But that's not how I am framing the problem. I am saying you restrict yourself to those microstates that have got a given value of N and V and E. Is this
independent in the sense that you can vary Each one
independently. I can give you, that's how I am formulating the problem, that you choose those microstates that have got this n, this v and this. It's like, so that's why I say a posteriori. It's not that the system, how to put it, like I can do it, like it's like the following, that these are independent, like as instances, they can be controlled from outside. You can define your system or ensemble this way, that I give you, these are values defined by me, n, v, e, then you do whatever you want.
No, the entropy, if you just look at the structure of thermodynamics, different thermodynamic potentials have different so-called natural variables.
Yeah.
The natural variables for entropy are n, v and e.
So how do you know? Do you know how to find the natural variables of a quantity? So you do ds. Yeah, you do ds. So you can just do, T ds is equal to what? So that's quite easy to. T ds is equal to du plus p dv. Well, the number is, you don't consider it, plus mu dn minus mu dn. So this at once tell you that s is a function of u, v and n. U is E. Okay, so that I should, I'll come to that. How do I interpret like energy in this setting? What is U here? By the way, you know this thing, right? That how to find the natural variable. So what you do is that you just write out the differential and you see what are the other differentials which are appearing.
Further, if you know S as a function of U, V and N, you know everything possible.
Yeah, I'll come to that. Okay, so let me just write out those. Yeah, so since you mentioned, so let me. Okay. So before I come to this equilibrium, so let me just write down. How do you, so now I have told you how to define the temperature in terms of entropy. Let me give you the definitions. You will find that you can, is how to interpret the internal energy. See, internal energy has to be interpreted because in this setting I don't know what internal energy is, but I know that it has to appear in the equation for ds. ds is equal to, so what you do is that, see, in this setting your total energy is constant. So therefore, S will be a function of n, v and e, and you just invert it. You express E as a function of n, v and s, and the function that you get is the internal energy. So you say that U, it will be a function of S and v, because you know that S is a function of n, v and e. Well, n is also there. Typically you don't write it because n is, okay, you can write it, I think. So that's just this one. So how do you get it? What you have to do is that you have to take, I don't have to even write it. So for a given system, a given system is specified n, v and e. So you compute, you find out the expression for S. S by definition will be a function of n, v and e, and you invert them and you express E as a function of n, v and s, and the quantity that you get, instead of denoting it as E, you call it U. Why do you not denote it as E? Because E is something that I give from outside. By definition, it's an independent variable. While U, from that definition, it's a function of phase. It's slightly bookkeeping kind of thing. So instead of calling it E, you call it U. It's the conserved energy of the system. That's simply put, it's just the conserved energy expressed in terms of S, V and N. Is the origin of the internal, just the energy. The particles are moving around. There is some the particles have kinetic energy. There is some interparticle potential. It's just the energy. Why is it called internal energy? Well, it's the it is not the like energy due to some external source or something. It's just the internal thing of the system. The particles are moving around. They have some energy. It's just, you call it internal energy. You can call it energy, but you call it internal energy. No, here there is no average. The average will come when you go to canonical ensemble. Here, the energy has got one given value, so there is no point in taking average. You don't have to take an average, because I have told you that this is my energy. So this is the internal energy. Expressed, you have to just make the dependence explicit. I mean, if you have to like average, you average with respect to what? No, at your ensemble says that all members of the ensemble have the same energy. There is no, you can take the average, but it's a trivial average. See, it makes sense to take the average when the quantity is fluctuating between the different members of the ensemble, of the collection. For this one, what is the temperature of Calcutta for the last 6 days? Okay, on first day, for every day it is 10 degrees centigrade or 15 degrees centigrade, then the average is, it would make sense when we come to the canonical ensemble, then it would make sense. The internal energy is really because the energy is fluctuating. I may have microstates which have got energy E1, E2, E3, and I take the average, that's the internal energy. But in this setting, you can do it, but it's trivial or something. Okay, so what were the other? So this is the internal energy. Temperature I have already defined, and the pressure is given by this formula. So del U del V S. Well, the way to do it is you first define pressure in terms of S with respect to V, and then you use the first and second law of thermodynamics, and you will get this one with this definition. So as far as the first and the second law of thermodynamics is concerned, all the quantities that appear there have all now been expressed in terms of the microscopics, namely gamma. Once I know gamma, or alternatively, as Musansi was saying, that once I know the entropy function, everything is defined. I have to just take proper derivatives and everything is done. So here S is really a very vital quantity, in the sense that I need to know it. If I know it, then my job is done. As it will turn out when we come to canonical partition function, it will not be S, but it will be the partition function. The canonical partition function. When I come to grand canonical, it will be the grand canonical. Okay, so now let me come to this postulate of equal a priori probability. So we have defined microcanonical equilibrium to be the one in which the phase space points are equal, they are uniformly distributed over the energy hypersurface. The hypersurface whose value is, the hypersurface is defined by solving the equation HQP is equal to E. That's the hypersurface. Okay. So let's look at it this way. This is my 6n dimensional space, and there is some. This is that hypersurface. HQP is equal to E. And the phase space points, they all lie on this hypersurface, and they are uniformly distributed in like any unit. I don't know what I should say, volume or area, but it's in that high dimension. I am going to find as many phase space points as at some other point. Okay, this is not the patch that I was drawing. I am just saying that that's what it makes. That's what it means to be uniformly distributed. And the microstates, the phase space points are the microstates. The microstates are uniformly distributed. What it means is that, so think of it in terms of probability. Okay, maybe this is a good way to. What do I mean by the fact that these points, points on this surface are uniformly distributed? What it means is that if I close my eyes and randomly pick a point, it's equally likely to be a point here or there or there or there. Equally likely. All the microstates are equally likely. I will not have preference in picking up some microstates which are which are close together here or there, because the microstates are simply not close to, it's not that there is a region where the microstates are crowded and there is one region where they are more sparsely distributed. They are uniformly distributed.
In reality, it's
It's not possible. maybe it's not possible. No, so that's what I am saying. They will keep changing, yet the distribution doesn't change. You may very well have a situation where things change. Things will change. I mean, of course, things will change. But it's a special state in which things change, yet the distribution doesn't change. And the distribution, the unchanging distribution is the one in which it is filling up the, it's a uniform distribution. What is a good way to, no, like, is this clear that you may have motion, yet the distribution doesn't change? So in this unit volume, let's say, in this unit volume, now look at my hand, in this unit volume there are certain number of particles. So I will say that it has some density. But it is not that these particles will continue to be there for all times to come. They will move out, some other guys will come in, such that the density does not change.
You have to go to Howrah station to...
You have to go to any stations. I mean, Howrah, more or less. In India now, now you see, in earlier days when we used to give the example of railway station, but now you can give the example of airport also. Now, in those days, only few people will be there with tie and so on going to. But now everybody goes to. You can the Dum airport maybe. No. Why why do you say constant current? I mean,
the things are changing, but given
that analogy, yes.
When two rods of a rod, two ends of a rod at an unequal temperature, there is a passage of current from one point to the other. But once they reach the equilibrium at a fixed temperature of the entire rod, then there is a motion between the molecules of the rod.
Yes, of course.
But
Yeah.
there is a
Constant current. Exactly. So that's the same example that I was he was giving, that let's say you have this situation. So this is not equilibrium, this is non-equilibrium. I mean, just to give you, I mean, this is a case in which in a equilibrium in the phase space there is no net current across any, but non-equilibrium. But these are like subtleties we will probably get clarified. I mean, or we can discuss once more. Okay, so here, no matter, so let's say let's consider the situation where TA is not equal to TB, where there is a motion. I just want to show that you can have motion, yet you may have a stationary state. So TA is not equal to TB. Let's say TA is greater than TB. So you have two thermal something at two different temperatures. So what it means to be in you should not say equilibrium, the correct word is stationary state, but let's say for the I don't know. So let's look at the situation where TA is slightly larger than where you are close to equilibrium maybe. So then, no matter how long you wait, you wait to make it, there will always be a net flow of particles from this to that. But you may still have a situation in which if I have an instrument here, some cross section here, the net current doesn't depend on time. So I'll say it's a stationary state. The net current across the, it's not on that when I have a constant current, as he said, it's not that things have to move.
Seebeck effect, thermoelectric effects, they come into this category.
This is much simpler than that. Yeah, Seebeck effect, you need like other things. Yeah, of course, this is Peltier and so on. So you don't have to you can think of it even of an even simpler situation. You have a resistance and you have a battery. So when you are in a stationary state, if you measure the current across any cross section, it's the same. It doesn't change with time. But of course, electrons are moving on. It's not that the electrons are, They are not sitting there. They cannot sit, because then you would violate the Hamilton formalism, classical mechanics. You cannot develop one frame, one subject of physics by forgetting another. It's simply not possible. It's a constraint system. It's a constraint. You cannot get rid of it by going to some higher ensemble. That is not possible. You have to. if you do it, then you have to say under these conditions, okay, these constraints are not going to be satisfied, and therefore I need to modify my rules. That's also, that's possible. In that way, you can forget about classical mechanics, talk about quantum mechanics, but you have to specify the conditions under which classical mechanics is not going to be valid. Here I haven't said any set any such condition, and therefore it's not going to. So what I was saying, this is this clear that this on the energy hypersurface, the very fact that the points are uniformly distributed, it makes you conclude that you would say that every microstate is equally likely, because the distribution is flat. If I had somehow a way to draw the distribution, so Mustansir had shown you some examples of a uniform distribution. So here, suppose x is a random variable, and I am drawing the distribution of x. So this is what you call a uniform distribution. The probability of getting this value and this value and this and that is the same. So you can think of this as the following, that if I blindly pick a value, it is equally likely to be this one, as this one, as this one, or as some other. And the very fact that the points are uniformly distributed, it simply implies that if you pick a, if you happen to have a way to sample the microstate, it is equally likely to be this one or that one, or in the whole zoo of accessible microstates. If you remember, I had this picture that there is a macro, this is a macrostate, and this corresponds to a whole this is the set of all possible microstates, and they all are equally likely. Okay, so this lets one to there is a different way to motivate.
So it is valid for the isolated system? Can we apply the same like we were doing in the microcanonical system?
This is an isolated system.
So this is isolated, but here we were saying that for the thermal equilibrium, there is a most probable state, means microstates. So there is a most probable microstate of the A and B, and they will attain that, then they will be the thermal equilibrium.
Okay, so this doesn't apply to this system per se, this applies to the composite system as a whole. I'll come to see, when I said most probable and so on, so I was considering the microstates of these of this system and this system, and they don't individually have energy values which are constant. Forget about, okay, so let me rub off this part. I'll come back to that. This microcanonical, I am going like even backwards in time in terms of my lecture, this thing. First, let us look at how do you define microcanonical. So what I am trying to do is to say that there is another way to motivate microcanonical equilibrium, then we will come back to that. Here, the fact that these two systems are fluctuating like energies, as you correctly pointed out, doesn't allow me to say that the density is uniform for individual microstate, like individual system, like obviously, because the energy fluctuates. So forget about this situation for the moment, we will come back to that. Let us look back at our definition of microcanonical equilibrium. We said that a microcanonical equilibrium is one in which the density doesn't change with time, moreover it is constant over the energy hypersurface, okay, for an isolated system. Why do I need isolated system? Because I know that for an isolated system, like energy is a constant of motion. Therefore, wherever the phase trajectories go, they are bound to lie on this surface, they cannot leave this surface. Okay. And then I said that the fact that the points are uniformly distributed on this one, this I did not, I did not give an argument as to why it has to be so, but I just said that look, this is a solution, a valid solution of the equation, equilibrium equation, let's say, let's put it this way. A valid solution is one in which this surface is uniformly filled up with, there is a uniform distribution of phase space points on this one. Okay. And then I said that you may put it differently, you may say that the probability is uniform on this phase, on this hypersurface. Okay. Okay, so there is a different way to motivate microcanonical equilibrium. So one way was to look at the equation for rho, and I say that rho del t is equal to 0, and therefore this is one possible solution, and so on. But I did not say why such a situation will hold for a system in isolation. Why all microstates are equally likely. This is a possible solution, but this is our solution, but I did not tell you why it is the solution, or why. So there is this postulate of equal a priori probability. So that says postulate of equal. So here I think the key word is this a priori probability. Now you have to go back to my lectures on dynamical systems and recall the definition of ergodicity. What did I say? What's an ergodic system? So it's a system in which if I start with a patch of initial conditions, then during the dynamical evolution, the patch is going to visit it is going to come arbitrarily close to any point in the allowed phase space. That was my definition. If you remember, I had said that for an integrable system, of course the patch is going to cover each and every, but then they all have to lie on this n-dimensional torus. That was the ergodicity on that torus. Generally speaking, when the system is non-integrable, you may have a situation in which somehow you are able to prove, and I will tell you that it is not possible to prove ergodicity for a general system. There are only a very few systems for which you can prove, but suppose there is a way to prove it. So ergodicity, what it meant was the following, that you start with a patch of initial conditions, a set of initial conditions. It is going, as time goes by, it is going to come arbitrarily close. It will visit, let's put it this way, forget about technical, it is arbitrarily close and so on. For all practical purpose, it will visit all possible points on the phase space, like allowed phase space, and for example the constant energy hypersurface and so on. Okay, so this was my definition of. So now if I somehow prove that the system is ergodic, then what I can do is that, so I would say that, look, if I have to take the average of a quantity, time average of a quantity, so what do I do? What I have to do, what does time average mean? So time average of some quantity is the following, that I have to look at the some quantity, let's say P of t. So what does it mean to take its time average? What it means is that time average along a trajectory. It's a, let me not use P, O, which is a function of P and Q. Remember that in our scheme of things, everything is a function of the generalized coordinates and the generalized momenta, and things have to be evaluated along the phase space trajectories, like gamma t. That's how things are good. That's why it's called a dynamical variable. So what it means to take its time average. So what I have to do is that this is a trajectory in this n-dimensional space, and I will evaluate it here and here and here and here and here and everything. I will just take its average. That's the definition of time average. Divide out by the total time. So if I have to do it this way, so this is time average. Well, technically speaking, I should take as long a stretch of time as long a stretch of trajectory as possible. By the way, this has to do with central limit theorem. I mean, the more points you take, okay, this is not saying that they are uncorrelated and so on, but it just says that the larger is the data set, it is guaranteed that the average will converge to a value. Like if you do it for 1 and 2, time 1 and time 2, I take its average. It is going to change as I make the time larger and larger. So the way it is defined is that so let's say I start making my observation from time t, and I go up to time t plus delta t, and then I put this quantity. This is going to, well, it may depend on time explicitly also. That is also not allowed. That also is allowed. Okay, so this is my definition of time average, where t has to be, technically speaking, I have to consider the limit t going to infinity. if for some of you don't understand why it has to this convergence theorem and so on, so you can do this experiment. I mean, I don't know how to motivate it, but maybe there is a way. I don't know. I mean, you see, as t becomes large, what will happen is the following, that actually maybe Devraj, you can show that numerical example that we did, no, for like illustrative purpose, that as you take, you are tossing a coin and you are counting the number of heads, and you take the sum. Yes, yes, exactly. That you see that like initially the huge ups and downs, and then so the why t has to be larger. You can do this experiment not for trajectory maybe, but for coin tossing. I mean, what you can let the computer do it. So if you look at this quantity, see this O time for a finite time, let's say for the finite time t of observation as a t. So you will see that like initially there is some, it's not so like periodic, but then like if t becomes larger, there will still be fluctuations which will not be visible on this scale. So they will converge to a value that doesn't depend on the value of t. It's just one of the nice properties of okay. So what you would do is that now it's about the time, but let me just finish this ergodicity business. So this is my time average. Okay. Now what I know for sure is that if the system is ergodic, then a single trajectory, this initial point, is going to visit each and every phase space point if given enough time, and I am indeed giving the system enough time. So what I can do is that instead of looking at it as a time average, what I can do is that I can freeze my time and say that, look, I have waited long enough, and therefore the system is not equally likely. I have waited long enough, and therefore the system must have visited all the possible microstates. They all are likely. So what I do is that instead of doing time average, I do a static average over some distribution of the microstates. It doesn't tell me that it doesn't tell me that all it doesn't tell me that all microstates are going to be equally likely, but I can do this substitution in the first place, that instead of doing this averaging along a trajectory, what I do is that suppose this is my like initial condition. So one possibility is this is my trajectory, I keep on evaluating it, taking the sum, and I do it up to this time. The other possibility is I don't do this thing, I wait for long enough, or let's say if the system is ergodic, then I am pretty sure that this same trajectory is going to visit all the microstates. So that means at a given time, at this time, all the microstates are possible. So I don't do that average. What I do is that I do the static time independent average over all possible microstates. I assign some probability to them. Somehow I have a way to see that these microstates are going to be visited more likely than others, and so on. This I can do. Why it is called so now see this I can do this substitution because I know that the system has visited all possible microstates. Therefore at a given time I can look at all possible microstates, I assign some probability. Suppose I had a way to find out which microstates have been visited more often than others, then I will input that, I will feed that information into my setting up of the static probability, and I will do this average. I don't know how to do it. For a general system, I don't know how to do it. What I would do is that in presence of complete ignorance, I don't know how to do it. The best thing is to say that, well, all possible microstates are equally likely here. And that's why it's a postulate. It's a postulate of equal a priori probability. A priori means it doesn't come out of calculus. It's not a posteriori. It's a priori. You assign this to be the beforehand, and then you do the calculation. It's not that you do the calculation and a posteriori you find that the probability is equally likely. It's a postulate. It's a postulate, and what you can show, see, first you have to understand that for a general system, it is very difficult to prove or demonstrate that the dynamics is ergodic. for a general, you can think of very simple systems like there are these billiard systems. No? There is a square or a rectangle, and there are these scatterers which are scattered around at random places, and you have a free particle. The rule is that each time this free particle hits a scatterer, it's going to have a specular reflection, that its kinetic energy is going to be conserved and momentum also will be conserved, and so on. And this will just go move around and so on. What you can show is that we have discussed it last time. If you remember my dynamical system class, I said that ergodicity that leads to ergodicity, then mixing that doesn't lead to mixing because it goes the other way. Ergodicity is the condition in which a patch of initial conditions is going to visit each and it will come arbitrarily close to all points in there. Then I came to mixing. Mixing, not just that it comes arbitrarily close, it is going to fill up every part of the phase space in the right proportion. I gave this example of rum and Coca-Cola or something that you use, that you have like initially the drop of ink that you put into this glass of water is concentrated at the location where you have dropped it. But then eventually, if you stir it well enough, it is going to fill up such that you will not be able to distinguish between ink and water. In every unit volume, you are going to see the same concentration of ink. So that's mixing. And the next part was chaotic motion. Mixing necessarily requires that this initial patch of initial condition gets so much distorted in time that it is it will get so much distorted that it is going to fill up the whole phase space. And chaotic motion was when I said that this distortion takes place exponentially fast. And if it is chaotic, then necessarily it is mixing, and of course it is. I don't know exactly the general statement, I could not find out one precise statement, but they say that if the motion is sufficiently chaotic, and I don't know what it means to be sufficiently chaotic. I mean, I did not even talk about Lyapunov exponent, but there are properties, I mean, you can put some bounds, and so if the motion is sufficiently chaotic, then it is mixing, and therefore it is ergodic. And if such a thing happens, then you can say for sure that this postulate of it's no longer a postulate, I mean it's still a postulate, but it is going to hold. Good. So the typical situation is, given a system, I don't know how to prove either ergodicity or mixing or this. What I do is that I have to make there has to be a starting point. And this is the best starting point that I can think of, because this is the most unbiased opinion that I may have about the microstates. This is a plausible assumption that I am not giving more weightage to some microstates. I say that all are equally likely. The other possibility is none of the microstates are, so that's trivial. Then of course I don't know how to do. The best thing, so one extreme is all the microstates are forbidden. Then that's trivial. The other extreme is all are equally likely, and this is. This is another way to motivate a microcanonical ensemble, that it's the ensemble made up of microstates, all of which are equally likely, and the system is in equilibrium. Okay? In equilibrium, not out of equilibrium. I have to wait long enough, and the idea is that if you wait long enough, the system will get to equilibrium. But these things cannot be proven on general grounds. Like for a given system, is there a way to check that this is? I cannot do like that. So the philosophy is that I take this as my starting point, I do the calculation, and this is consistent with all the constraints like del rho del t plus rho h equal to 0. That is, I do the calculation, I get to a point when I have a measurable quantity. I get an expression for that measurable quantity. I make my measurement. If it works, I will say for this system equal a priori postulate of equal a priori probability holds. You would like to make someone? Okay. Okay. I mean, please understand that proving ergodicity, and especially for one particle itself is a huge amount of work, and for interacting particles, it's kind of you cannot even think of doing it, because it's the motion which is taking place in this very high dimensional phase space, and then it's impossible to do it. And of course, it's impossible for, especially, I don't know, with maybe with some math, the papers in this. By the way, I forgot to tell you that this part of the theory is, this is part of the subject. It's part of what the mathematicians call like ergodic theory. There are many. I think Professor Dani is one of the important contributors. And if some of you are interested, so Professor Dani is coming here in January. He is going to stay here, not to physics department, to the maths department. There is a conference on dynamical systems. So he is going to stay here for quite a long time. So if you are interested in finding out, you may come back again. January is going to be even more cold, but okay. Okay then, yeah.
This is a typical thing we do in physics.
Yeah.
We have to move ahead.
Yeah. You have to have a starting point. I mean,
this is the starting.
This thing is the starting.
And it turns out it is wildly successful.
Yeah.
Assuming this, we deduce some result and they match, most of them match.
Exactly. But that doesn't tell me that this thing is wrong. It just tells me that this is going to hold, this holds for this system. So that's why it is still a postulate. A priori postulate. So that's why something that you assign at t equal to 0 and then prior to everything else, not a posteriori. You do the calculation, then you think back, okay, this.
I mean, we are being honest.
We are being honest.